Okay, so that first arc was set up, I think, mostly. Now I think we'll try and do a little bit of math, and then we'll go back and do some more code. And we'll alternate math and code, I think, until we run out of time. The problem that I think I've talked about the most here so far is the idea of a propagator, which I've given without definition. I said sort of briefly monotone functions between joined semilattices, but I didn't unpack what that means. So let's first talk about what a joined semilattice is. How many people in here are comfortable with the concept of, say, a monoid? Okay, I actually got unilateral everybody up on that one, so I will just assume the concept of a monoid. We have an associative operation with a unit. If you add commutativity, that AB equals BA, now you have a commutative monoid. If you add idempotence, we have AA is A. What are examples of a, I knew he was going to what are some examples of a joined semilattice? The integers with, or the naturals, because we need to, I want a zero, I want a mempty. I want a bottom for my lattice, for my joined semilattice. The naturals with max work for this.
Adding the idempotence, that gives you the joined semilattice?
Idempotence on a commutative, that's all it is. Okay. Idempotent commutative monoid.
I missed that, and then you were talking about.
Yes, idempotent commutative monoid. So I'll say a join semilattice is going to be an idempotent commutative monoid. So we know AA is A. We know that A bottom is A, bottom A is A. ABC is ABC, no matter how I put my parentheses. And AB is BA. And I'm just going to use juxtaposition for right now for talking about the join operation. And I will talk about this. Once I have this notion of joined semilattice, there's an associated ordering that comes with it. I will say that x is less than or equal to y is going to be equivalent to saying there exists a z that I could smash into, I could join with x such that xz is y. So there's some element that I could join with x to get to y. And so we're going to visually draw we'll say the later things in the joined semilattice, y will be above x in the diagram somehow, if I ever draw a picture.
It's a partial order, right? It doesn't say anything about x.
Yes, it's a partial order. So far so good. So every joined semilattice will give rise to a partial order that may or may not be constructively realizable in Haskell or something like that. But this is what it means to be less than or equal to. Now that I have less than or equal to, I can talk about monotone functions. A monotone function says something like, well, if x is less than or equal to y, this implies that f of x is less than or equal to f of y. So f is monotone when increasing my inputs can only increase my outputs. They might stay still. This is not strictly monotone. Like this could definitely increase while this one stays the same. But that's what I mean by a monotone function. is it increasing the definedness of my, or increasing the amount of information I have about my inputs. I'm increasing the information I have about my outputs. Now, if you are familiar at all with Scott domains or domain theory, like the sort of the world of denotational semantics that we start talking about when we started talking about the semantics of our programming languages, that less than or equal to is more defined than, or is less defined than or more defined than kind of relationship, has all these properties that we've talked about so far. And as a matter of fact, we may be able to play around later on with lifting Haskell combinators into propagators just by exploiting the fact that in Haskell, all functions are monotone in this respect with respect to their inputs. Not every monotone function between their inputs can be provided, but we have bottom that sits below each one of our values in each one of our types. So bottom is, we use it for non-determinism, like for any time we throw an exception, whatever. It's like denotationally bottom. But if you give me an answer for bottom, then you better give me that exact same answer for true or for false. Because we can view the Booleans in Haskell as bottom with true and false here, sitting above them in a partial order. The definedness order. That doesn't say how true and false relate to each other, just that true and false are more defined than bottom. So if you give me a function and it returns true for bottom, then it must return true for true and it must return true for false, because there's nothing more defined than true in the little order that I have available to me for definedness in Haskell. So we use this. So if you start trying to count Boolean functions in Haskell, there's more of them than you'd think. A function from bool to bool. But they still have some structure forced on them. They can't just do anything with respect to bottom. One of the reasons why I like laziness over strict languages is that you don't say what to do for null when you're given a null argument. You just, the behavior follows from, the undefined behavior follows from how much you do case analysis and whatnot. You can return non-bottom given a bottom in a lazy language, but you're not sitting there special casing and treating null as yet another third first-class value that you have full power over. So it helps shrink the space in some ways and grow the space of programs you can in another. Okay, so I don't know that that tangent was terribly useful. But let's look at some joined semilattices, shall we?
Can I
yes.
Ask this true and false, so they're bigger than bottom in some
Yes.
ways? If you look at the first example, so x smaller than or equal to y, if x is bottom and y would be true, what could z then be?
If x was bottom and y was true, I'm going to join these things by moving up to their least common ancestor in this thing. So I'm going to make if I want to make this a joined semilattice, I have to be careful. I need an extra element at the top. You've told me it's both true and false. Blow up the world, contradiction. So normally the symbol for this would be a top symbol. Unfortunately, that looks a lot like a true. So I'm just never going to draw the tops on my lattices. Okay? Envision that there's this little imaginary contradiction node up here. And then I'm going to wire this up with my propagator network to say, hey, look, if you ever reach the contradiction state, blow up the universe you're in. Don't go to the top. This is going to be the way that I handle contradiction. So now what we have is this. If x was bottom and y was true, and if x is bottom and y is true, then z here would be true. If x is bottom and y is false, z here would be false. It's boring in this case. And if you give me, if you try and tell me something's both true and false, contradiction, blow up the universe. We go to this top element of the lattice, which is not representable in Haskell's types, because it doesn't come up there. We don't ever try and tell you the value is both this and that. It would come up in something like if you used unamb incorrectly using one of Colin Elliott's constructors for doing unambiguous choice for racing things. That's about the only time you ever see this idea in Haskell.
Would representing that in the type system require subtyping?
That's one way to start trying to talk about this. Like in Scala, you can talk about nothing and any or something like that, but it's not really any. These are values, not types. You're starting to get the flavor of it, but it's not exactly the same thing. Some of these lattices for me are things like, hey, I've got one down here, bottom, 0, 1, 2, 3, 4, or I can even just start at 0. Let's call 0 the bottom of my lattice. And I'll just keep going forever, and I'll join with max. It's a fairly obvious one. Another one might be where I have a single layer. I have bottom, which is I don't know anything about it, or I know it's exactly -1 or -2, -1, 0, 1, 2, 3. I have the integers. I have a thing that's one layer tall plus a contradiction node at the top, where I blow up the universe. And this is sort of, if you know what an IVAR is, or a promise, I would use this encoding to represent one of those. Using Lindsay Cooper's variation on the idea of a promise, where in her case, you're allowed to fulfill a promise multiple times, so long as you fulfill it with the same value each time. If you don't know what a promise is, I can unpack that in a minute. But so this is like, these are kind of two extremes. One is this chain, and one is this sort of anti-chain, where I've bolted a bottom and a top onto the anti-chain. An anti-chain is a bunch of elements that are mutually incomparable in order theory. And we can come up with all sorts of things that don't look like either one of these extreme examples. Is this not sticky on the top? It's not. Okay. Lindsay Cooper? What about? Oh, her name? I don't remember how to spell Lindsay, I think. Lindseykuper. So she has a language, or a little project called Elvish, which is a project for working with these things she calls LVARs, or lattice variables. And her lattice variables are join semilattices, where she has computations that you're allowed to fork, and you're allowed to read and write to your lattice variables, but when you write to a lattice variable, whatever you wrote into it will be joined with what's present, using the join of our join semilattice. But when you read from the lattice variable, you're only allowed to read under a very rigorous discipline, where you use something called we're going to use these disjoint filters over the data set. They're like these funny little traps that you can wind up stuck in. And I'll talk a bit more about the Elvish style of reading from a propagator, because it turns out, or not from a propagator, from a join semilattice, because it turns out that everything that I can write in Elvish will be a monotone function, and therefore everything that I can express in Elvish, in her, yes, will be a valid propagator. And it also turns out that Elvish is a good vocabulary for talking about coordinating problems, where you've got variables, where I take her notion of a cell, like a variable, and I use it as one of my propagator cells. And then I wire up propagators between them to kind of give Elvish extra superpowers. Okay, so for me, Elvish is sort of a coordinating language for working with propagators. Not every propagator problem that I can express is a valid Elvish program, but is a vocabulary in which, as long as I speak this vocabulary, as long as I can speak Elvish, thank you, Tolkien, I will be able to write valid. I knew that skill set was going to come in handy someday. I'll be able to write valid propagators. Cool? All right. So I was going to give a slightly more worked example. We could talk about a product of a pair of Booleans as and then I'll use this as a motivation for her funny reads. So right now I've got a pair of Booleans, so I've got my bottom. I don't know anything about either one. Then I could learn that the first one is true, but I don't know anything about the second one. Or I could learn that the first one is false, but don't know anything about the second one. Then I could learn that the second one is true, or the second one is false. So each one of these is more defined than knowing nothing about either one. Correct? So I could learn that both are true, and that's more defined than that, and it's more defined than that. I could learn true, false. I didn't choose good orders on these things. False, true, or false, false. And then if I get this right, each of these things should have 2 arrows into it from below. And then false, false, right? So that lovely little lattice, or join semi-lattice, with an extra contradiction node up at the top, it would be a product of these two of these little Boolean lattices. Okay, so what could I do with this? Well, let's say I wanted to compute and as a monotone function from here. What is the moment at which I know that and is true here? Like I've got these 2 variables, I want to apply them, right? I know that this is true in this situation, in the true case. This is definitely going to be true. Everything about, like, from there up. Okay? Here we know that the answer is false. But these 3 cases are not the only cases in which we know the answer is false. We also know the answer is false all the way down here, the moment any one of the 2 inputs is false. So I can come all the way down here, and these are the things I'm going to be yielding false for. Now what's interesting here is that each one of these elements that's in this trap here, this what's called a filter, every element that is greater than an element that's in the filter is also in the same filter. Like this thing includes the contradiction node. This thing includes the contradiction node. Everything, these are upward closed subsets of my set of states that I could be in. Does that make sense? So the clever part, or one of the many clever parts of Lindsay's PhD thesis, was that as long as these filters are disjoint, or in this case only intersect at the contradiction node, there is no reordering of learning facts that could cause me to go from one trap into the other that doesn't involve me blowing up the universe. That doesn't involve me reaching contradiction eventually and then stopping the problem. So the idea is, like, if I learn that the second child was true, or I learn that the first child was false, in either order, I get the same node in the same graph. I'll eventually wind up in the same trap. So what she does is she does these she has computations that you're allowed to run forward. You're allowed to fork. So you can create multiple threads. And the way that your threads can talk to each other is they can create, you first create a version variable, or you create one of these lattice variables before you fork. And then I can see other people's writes to these variables as long as I only read with these upward closed sets, these filters, using disjoint filters. And the way I do it is I block until I land in one of these traps, and then I give you the answer that I've associated with the trap. So in this case, I can block waiting on this pair of Booleans until either both are true or until either one is false. So this would be how you would build this using Lindsay's vocabulary of threshold reads. We've crossed whatever the thresholds are below these things. And everything above that point must yield the same answer. So you have create variable, fork, write to variable, where you do a write by using the join of the semilattice to merge your answer into the semilattice, and threshold reads. And now you can think about this as, why is that every attempt to use one of these things monotone? Well, any attempt to write to a variable in her vocabulary can only increase what's there. Okay, so that can only cause the output to go up. But any attempt to read will block until she lands into a trap, in which case it has no effect, or it has more effect than it did before. That's it. It's clearly, obviously monotone, every program that you can write in Elvish, no matter what concurrency framework you add on top of it. It works very, very cleanly as a building block for writing propagators. And then in my case, I can bolt propagators to push information between these join semilattices as well. And so what I'm going to do is give a sketch of what that is even about. So to me, a propagator network. Oh, and I should do one more thing on this before I go on the tangent. Yes?
I have a question. Have you ever thought about using this for when, instead of having notion of definedness, you have notion of already being computed?
Yes. Yeah, we're going to have to close the door. So this lattice was really complicated, right? Did you have a different one?
Real quick, is there a paper that covers the application of the propagators?
No.
This is something you've got in your
Yeah, this is me.
Okay.
Yeah, this is me. This is a thing that I've given a talk at, I think, Yale West that was been recorded that's online. That's like a hour-long introduction to the topic. I've given a talk, I think, at Yale Lambda Jam as well that also talked about it. So there's a couple of varying degrees of expert level introductions to the idea of propagators, and a laundry list of about 120 problems, I think, that I enumerated that kind of fit into the framework. It was a bit exhausting. All right, so we've got this notion of upward closed trap. Can I approximate that by using, let me see if I could write that thing, that function on products of Booleans, using the par vocabulary. Okay, and just very simple, individual Booleans. So let's try and let's sketch a parallel program, what it should do to read from a pair of Booleans and write out a Boolean as a monotone function. So what I have is I have a lattice over here, and I have a lattice over here, and I have a lattice down here, which is going to be my result. And what I want to do is start a computation and fork. So I have two threads of execution that come in and go out two different ways. The first thread of execution is going to block waiting on the trap. Is this thing true? And if it gets yes, it's going to come over here and block waiting on the trap. Is this thing true? And if it succeeds, it will come down here and it will write, yes, I'm true. On the other hand, this one comes over here, and I can, you know what, we'll go back to that first computation. We can add another trap to it. Are we false? In that case, come down here and just write false immediately. Done. The second computation just comes over here and blocks on false, and immediately writes false. So we did a fork, one threshold read with two thresholds, and another threshold read on the other side with one threshold, and if this one's returned true, we do a threshold read here. So there's two threads of execution pushing information around between these joint semilattices. This would be an Elvish program for pushing information from these pairs of individual joint semilattices to a larger joint semilattice. I like this program better than that one. In that case, she had to build one big joint semilattice, and even if there was no information gain, no progress being made, you were waking up and trying to push information towards the output and like wasting time. Here, every step is actually like every time you're told about a change in your input, you're actually making progress towards your goal. We're incrementally running the program over these smaller traps. Another example of a joined semilattice might be something like, here is a set of names. And every time you give me a new name, I will just insert it into the set. And then one of the upward closed filters might be, is Bob in the set? Like waiting until Bob becomes a member of the set is a thing you could do, but now that propagator is going to like wake up and try and push its information out every time you add anybody to the set, which seems rather grossly inefficient. It's going to wake up too often. And waking up too often is a general kind of propagator problem that we're going to try and mitigate by stealing some techniques from SAT solving. So far, so good. So we've got break my problems down into smaller pieces, use Elvish as a compositional vocabulary for building the propagators. In Guanxi, what I have is sort of the guts of a propagator framework. It's all of the things are built with very many wires exposed. It's not designed for inexpert use at this point. I'm still trying to figure out what the vocabulary should be for an EDSL that exposes these parts. Right now, I'm trying to make sure that I can write the logic programs that I want, and then I'm going to try and gradually bring it down to a scale where like other people can hold onto the pieces and use them without cutting themselves. Okay. Another example for that set size thing is, are there at least 500 names in the set? You know, like that kind of filter is a trip. You'll trip it eventually. So these are kind of classic examples of what would be like a CVRDT, if you're familiar with the convergent replicated data types, of like sets that gain membership. Boolean flags like this, these promises that are lattices that have one level, or joined semilattices. When I say lattice, just hear joined semilattice. If I ever mistake it, it's because I screwed up saying it, not because you missed a step. Each one of these lattices has one level above bottom, and then I blow up the universe. This is a fairly common pattern, and you can view this as a promise. This is a computation that may or may not happen, but the moment it happens, I've got the value, and that value is good forever. That thing has different names depending on who you ask. It's either an IVAR or a promise. Both of those are terms for the same idea, except for the fact that normally you're not allowed to fulfill a promise multiple times, even if you fulfilled it with the same value. Whereas in Lindsay-Cooper semantics, you're allowed to fulfill it multiple times as long as you always fulfill it consistently. And it's an error to fulfill it inconsistently. It's good and bad in some ways. You kind of need the ability to compare things for equality, so you can't give me a promise of a function unless you just say, trust me. Here's an unsafe fulfill promise call or something like that that will just believe that you don't screw up. So you have to be able to compare for equality in order to use Lindsay semantics, or you have to give me some unsafe operations for working with promises. And then, again, for reading from one of these things is, do I have a value yet or no? And I just block waiting until I have a value to read from under her model. So you could implement these things like with an mvar behind the scenes or something like that, and then have the thing block waiting to peek at the mvar. And then putting into the mvar would scribble this thing in here. And it should be careful about trying to put in when there's already a thing there. So that's why the Lindsay-Cooper semantics get complicated for that. OK, so we have joined semilattices. What I want to do is so overall, I have some propagator network, which has a bunch of nodes. And each one of these nodes is a joined semilattice. What do I know about a thing? And what I want to do is have these propagators that push information, possibly with multiple inputs, into other nodes in this graph. And what I would like is a set of sufficient conditions under which it doesn't matter what scheduling strategy I choose, I should yield a deterministic answer. And by scheduling strategy, I mean this. As long as I gain information in this input, all outputs from it, all propagators that are reading from this input, should eventually fire before I consider the network to be at rest. So what I'm going to do is I'll pick some scheduling strategy that just ensures, like, put them into a set of propagators to do, and then just make sure that everything in the set gets run eventually. And my goal is to find strategies, find good orders to evaluate them in. Just because there are some things are not all orders are created equal, even though they should all be determined. I want a set of conditions under which it doesn't matter what order you choose, and then once I've got that, I want to find a good order anyways. These are kind of the two major steps, I think, in making propagators practical to me. And to understand them, we need to view a couple of different problem domains as propagator problems, then steal the things that we've done as foundational research over the last 30 years to make those individual domains fast and transfer them to other propagators. And this is the lingua franca. This is the tool that I think was missing from Alexi's thesis. It's not just, hey, these are all propagators problems, yay, go, but how do I transfer all of the knowledge that we've gained institutionally? How do I use it as a bridge? Like I use category theory to steal things from one area of math and transfer it to another. Yes?
When you have these multiple inputs, do you need to make sure they don't conflict?
I am effectively a propagator from the product lattice of these two things. Given a joint semi-lattice, there's a product joint semi-lattice. It's like I can look at this many copies of this semi-lattice as a semi-lattice itself. Effectively, like when I drew this lattice of true and false, all the ways that pairs of trues and falses could be glued together, and this is effectively the product of these two lattices. It didn't require me to worry about them conflicting at all. I'm able to read from this product of lattices.
So like one of them writes into the first element,
and one of them writes into the second element, and we are less than or equal to you if like we're less than or equal to you on both sides.
but both are not writing into the first element.
Correct.
Okay.
So this propagator is like reading from different things. So example, we can go back to the promises story that we had, and I could have the value is either bottom or it's exactly blah. And then any Haskell function, I could basically just or any total function, I could just look, are all my inputs defined? Great, then just feed it to a normal function and produce the output, and then that goes from bottom to exactly this value. So I can lift an arbitrary normal function as we know it, function from A to B to C, and do something from promise of A to promise of B to promise of C. So you can lift normal functions over promises. So there's like an applicative style structure there, even if you can't quite make the instance. So far so good. We've got propagators. We've got the idea of getting some big network that has a bunch of stuff in it. One of Alexi's examples involves like setting up a network of, you've got Celsius at one end and Fahrenheit at the other, and you're going to do this multiplication. And this division is set up in such a way that we can propagate forward and backwards through multiplication or division. And unfortunately, the example that he gives there is somewhat sloppy in that it's not really possible for you to ensure that you get exact results through it. It like computes intervals, that those intervals contain the answer, but they're not the tightest possible intervals. So he's got a propagator network, but he doesn't have necessarily the best possible propagator network for the class of problems that he works with. I will typically use these things with, like I said, interval arithmetic, where I'm going to push information around. And then when I get down to the end, I'm going to start guessing examples, like to do finite domain solving or something like that. You give me that x is between 1 to 5. You give me y is in the same range. The moment you tell me that x is strictly less than y, I gain information here. Just from this constraint alone, I can immediately learn that x cannot be 5, It can be at most 4. And y cannot be 1. It has to be at least 2. Right? So establishing arc consistency, even before I try and guess, just like we were doing with the SAT solving thing, before I even try and guess, I just establish this consistency with this local condition. So I can have x and y here as variables with a x is less than y edge on it. And these variables here represent intervals of like these are sets of integers with intersection as the join semilattice. And then what I'll do is this. When I do finally, I'll run this thing until I can't propagate anymore, and then I'll start guessing. So Guanxi is basically a propagator network plus non-determinism to allow me to do guessing. So then I will guess, hey, x is 3. And the moment I guess x is 3, we now know that x is less than y, so we should propagate and learn that y is between 4 and 5 in this universe where x is 3. So now I only have 2 cases to enumerate for y. So if I'm forced, because nothing else is going to propagate and narrow my range for y, we're good. And if I ever run out of things for y, I blow up the universe because we're at the contradiction state. There is no possible assignment for y. We blow up the universe, we backtrack, and we stay out of that place. So this would be how you would use this for, say, finite domain solving at a very loose sketch. So less than or equal to is a relationship. We've established that we can take, like if I knew the exact value, I can add addition nodes and stuff like that for pushing information around here. And if we start talking about other forms of abstract interpretation, we can get more and more stuff captured in sort of raw form by a propagator, trying to minimize the actual amount of case-by-case enumeration we can do. How much can I just reason by carving off half spaces or something? Is the polytope inhabited? Yes. Okay, then we're going to continue believing that this universe is plausible until I absolutely am forced to enumerate things. So now, one condition under which I can trust this network to always terminate and yield a deterministic answer, even under no matter what scheduling strategy I pick, is for all, the simplest condition that I could come up with the first time I tried it was to say, if all of my lattices, of all my joint semilattices are of fixed size, or of finite height. Okay, if there's a maximum height on every joint semilattice, so everything looks like the one that we had over there. We had x, bottom, true, false, contradiction. If everything's like height 3 at most, then you can only go up so many times. You can only increase information so many times. So each propagator can only fire so many times before we have to blow up the universe or stop. So if my propagator network is finite in size, and each one of the joint semilattices is finite, and I'm not dynamically adding nodes, then my propagator network will terminate. And by using the idempotence and commutativity conditions that we've talked about earlier, it doesn't matter how many times I redundantly fire a propagator, and it doesn't matter which order I choose. So I need the monotonicity, I need the commutativity, I need the idempotence. Each one of the components is a portion of this story. I need to know that I only go up so many times. Otherwise, I can build a propagator network that says, we've got the rationals with intervals, and I can build a propagator network that spins through and computes closer and closer rational approximations to square root of 2 as intervals. It gets intervals that get closer and closer and closer and closer and closer. And this propagator network will never terminate. All it's doing is doing Newton-Raphson iteration steps just as a propagator cycle. It will continue to get me closer and closer answers to the square root of 2. But I don't know the rate at which it's converging and all this kind of stuff. So I can still use the propagator network. It just doesn't terminate. So I would have to have some other condition or some other way of managing it. The subset of Rudoul's thesis that I actually am kind of engaging in is the case where I believe the system is going to terminate and yield a deterministic answer if it terminates at all. Like I'm willing to allow non-termination in some cases because like it's useful to be able to talk about x from minus infinity to infinity, even if sometimes adding propagators in there means that I might have to give you an infinite family of solutions or try and enumerate an infinite family of solutions. Yes?
Could you use something like weakening in the infinite case?
Yes. So we can. There's a form of weakening that comes up that is, if I'm using the term in the same way that you are, where if there's nobody that's listening to that variable, I can tell you how many copies of a solution there are and just kind of forget the variable. If there's no propagators out of a variable, and if I'm not looking at it at the end, I can just tell you that there's, oh, that was an interval from minus infinity to infinity. There's now, if not extra many solutions of whatever I just solved over here. I don't know if that's exactly the sense in which you're using the term.
Well, from abstract interpretation, you can, if you have like an infinite thing, you can.
Okay, the widening operator. We'll talk about widening in a minute. And one of the reasons why I had Presburger bounds earlier and talking about like complexity 2 to the 2 to the 2 to the n was because one of my things was to avoid widening. Yes, I see it. Yes.
Can you artificially fix the height of the lattice?
Sometimes, not always. The integers with max don't have a bound on the top.
But what if you were to have, so if you only treat integers, yes, but you showed an example of tuples. What if the other bit of a tuple is an index? That's the depth, and you just assume that the moment it goes above certain.
Yeah, there's lots of ways to hack this in. I mean, this is a sufficient condition. It's not a necessary condition.
Okay.
So this is the simplest sufficient condition. I wanted to offer it up because we could finish it before we ran out of time. The next most interesting sufficient condition is something called an ascending chain condition. All I require is that all paths upwards through the network have finite height. All paths upward through the network eventually hit a fixed point. Each one can have a different length. They can be longer and longer and longer, whatever, but they all have to be finite finite length. That is also a sufficient condition under this system. And then for like example for data log, what I do is I take data log uses the fact that there are only so many source facts. Like Bob is a parent of Nancy. Like I only have so many names mentioned, Bob and Nancy, this, that, and the other thing. I have no combinators for building fresh names. And therefore, at most, every name could occur in every position in every predicate. And I'll eventually exhaust the space. So even though there's nothing bounding the height of how many rows there are in each table, the source data gives me my height bound. So my propagator network for data log has that similar flavor. So I don't think we're going to have time today to do the snippet that I wanted to do using, like, exploiting the structure of SAT to get a 2-watch literal scheme to wake up my propagators less. So I think what we'll do is we'll pick up with that, I guess, on, is it Thursday morning? Yeah, or Thursday morning or Thursday evening, whenever the next session is. And I think we're just going to keep spending more time on propagators because I think this is the most juicy piece here. And then from there, we'll transition into the rest of it.